Hello, the topic for today is integration, namely a definite integral. Now in calculus we learned a trick for that. We find antiderivative and then we substitute upper limit, lower limit, subtract, we are done. In applications this is not always so easy, in particular because the function f itself need not be given as a formula but rather as a collection of, let's say, measurements. But even if it's a formula, still the situation can get really complicated. Here is an example, and it's a famous one. Let's say that you want a definite integral from the function e to negative x squared. This is actually a very important integral, and statistics relies on it heavily. However, the function e to negative x squared as a continuous function has antiderivative. It's a nice function, but it cannot be written as an algebraic formula, or closed algebraic formula to be precise. And if you don't have it as an algebraic formula, then you cannot substitute in limits and do the usual trick. So for this type of integral, the calculus approach does not help, but we need to know the value. So there is a big demand for numerical methods that would help us evaluate or approximate definite integrals. This is actually one of the oldest questions in numerical analysis, and it used to be called numerical quadrature or just quadrature. How do we do it? Well, actually we take inspiration from the definition. Let's have a look at it. Here we have an interval AB. There is a function floating over it somehow. And we are interested in the area under the graph. And definition says that we should look at partitions. Partitions, it means that we split the interval AB into segments. And over each segment, we are supposed to erect a rectangle of a suitable height. And then these areas are put together. There is some limiting process or supremum infimum process, and it works out. It's a good idea, but it's not practical because there are too many possibilities. So if we want to do something applicable, we have to restrict our attention to nice partitions. Namely, we are going to focus on partitions which are so-called equidistant, which means that the segments are all of the same length. And if you want to take an interval and divide it into segments of the same length, you need to know how many of them there are, and that's it. That's all the information that you need to start with. So lowercase n, that's the traditional name for the partition size. And when you split interval AB into n equal segments, then the length of one segment is easily calculated. It's just the length of the interval divided by the number of segments. And that's a very important formula. I'm emphasizing it in this way because I will be returning to it repeatedly. Okay, we have our step size. And when we have the step size, we easily determine the points of the partition. We can even write it down as a formula. How many of them are there? That's a good question. If there are n segments, then you have left endpoint for each of them. And then there is an extra point which ends the last segment. So there will be n plus 1 points, and it makes sense to call the first one x0. So that will be the A, or x0. And then there is x1, x2, and so on. And you can see the partition size h over here. And the last point happens to be xn, so everything fits very nicely. And for each of these points in the partition, you get function value. And that's the data that we want to work with. And again, this is really tied to the real-life applications because typically, when you have some function, you know its values at regular intervals. That's a natural way of arranging it. For instance, let's say you are interested in temperature, so you set up some measuring device and records the temperature, let's say, once an hour. So you get nice, regularly spaced values of your function. This is called sampling, when you have a function known just by values. So we have a sample of our function, and a good question is, how do we use it to actually approximate, and now we are talking not about limit, but about actual number. How do we approximate the integral? Let's call it capital I. Well, let's have a look at a better picture with just small partition numbers so that we can approximate or appreciate better what's happening. Here we go, our function f, and let's say that I use partition size 4. So here is 4 segments, easy to do, easy to arrange. And now, when it comes to numerical integration, the focus is on one panel, which means on one strip. Okay? So here is one strip, and I actually have just two pieces of information here. And my motivation is to find a rectangle which is a reasonably good approximation. Since I have just two candidates for the height, I will choose, let's say, the left one, because it's, well, I see it right here. So I use left rectangle, so to speak, that's how it's called. And that, I hope, is an approximation that is not totally worthless of the area under this part of my function. Okay? And of course, I'm going to do the same for all other panels. Each time I'm using the value on the left to find the approximation of the area under the graph. And when I put all these areas together, I will get an approximation of the area under the function f. So the formula goes like this. The integral I will be approximated by the area of the first rectangle. The base is h, and the height is f at a, but it's better to write f at x0. This is the area for the first rectangle. And then comes the area for the second rectangle, h times fx1, and so on. And the last one, let's imagine that the partition size is n now. So for the last rectangle, I'm taking base h and multiplying it by the value at the left point, which is the second last partition point, f xn minus 1. And that's the approximating formula. There is a name for this idea. This is called the left rectangle method, or left rectangle formula, or left rectangle rule, and so on. Okay, let's try it out. So I have an integral example. From 1 to 9, I'm trying to integrate logarithm x dx. Okay, do I like this integral? Well, actually, it's not bad. Antiderivative to logarithm can be found in books, or you can determine it by integration by parts. But let's say that I don't just feel like integrating by parts at the moment, so I apply left rectangle method and see what we get. Partition size, let's say 4. We had a good experience with 4 over here, so why not? And then the step size will be the length of the interval, which is 9 minus 1, which is actually 8, divided into 4 pieces, gives me 2. That was easy, wasn't it? Okay, now let's see. It's actually not a bad idea to draw a picture when the partition size is reasonably small. So here's my interval 1 to 9. I'm splitting it into 4 chunks. So now even common sense tells us that the step size is 2, and the partition points are 1, 3, 5, 7, 9. Okay, let's see. The integral will be approximated by, and I'm going to substitute, and actually it's a common practice to factor out the step size so that you don't have to keep repeating it all over. So I am factoring out the step size too, and for the first rectangle it's base times the height at 1, which is logarithm at 1. I'm just substituting. For the second rectangle, it's base 2 times the height at 3, and 5, and 7, and I shouldn't overcook it. 7, that's the last one. Okay? For the last rectangle, value on the left. That's it. And yeah, that's it actually. I just approximated the value of this definite integral using the left rectangular method. Very easy. If you encounter it at the exam, you will rejoice most likely, and you can leave it like that. Actually, I appreciate it if you leave it like that, because I look at it and I see what you did. So you don't really have to worry about telling me that logarithm at 1 is 0, or putting it together using some identities, whatever. Yeah, I leave it like that. I like it. Natural question. Why left rectangles? Why not right rectangles? Well, why not? Okay, let's have a look at it. Here is my interval AB. Here is my function, f. Here is my partition size 4, my strips, which I now call panels, to sound scientific. In the first panel, I will use the value on the right, and I am getting a rectangle like that, and the area of this rectangle is the base times the value on the right, which is x1. So this is the area of the first rectangle, plus the area of the second rectangle. Here I'm taking the height on the right, and the area is h times f at x2. And I keep going, and I keep going, and I keep going. And the last rectangle, let me get to it. The last rectangle has base h, and height is at f at b, which is f at xn. Here we go. So that will be the right rectangles. And you can attach the name method, rule, formula, whatever. Okay, before we move on, let's have a look at this picture. What I'm actually doing, I can be thinking of it as approximating area by another area, but I can also see it this way. I took the function f and I replaced it with a step function. Here is a step function, and here is a step function. Step function means a function which is composed of segments which are constant functions. That's also a useful point of view. Okay, so here is a slide which confirms that the left rectangle rule uses the formula that we can see on the right. We factored out the step size h and we got this. And there is also a summation form for those who like summations, which is nice, compact form. Nothing wrong about it. And it's called RL, R for rectangles, L for left. No problem there. By the way, this notation is not totally universal, but many people use it. And if I scroll, I get a formula for the right rectangle rule, which again agrees with what we did over here. Essentially, those rules are more or less identical when you think about it. Especially if you imagine that the partition size is large, then majority of the terms is actually shared, starting with x1 and ending with xn minus 1. This middle segment is common to both formulas. They just differ which part they ignore. The left rectangles, they ignore the right endpoint, and the right rectangles, they ignore the left endpoint. So when you think about it, when there is like 100 of these terms, if you ignore this or that, it doesn't make much difference. So expectation, intuitive expectation is that these two methods should be essentially identical in, let's say, practical work, in practical behavior. Let me actually finish the example. So if I want to use the right rectangles, I should skip the first value and just use the second, and so on, and I keep going, and I stop when I get to the last value. Okay, so that would be the right rectangles. And now here is place for another example. I don't want to use the logarithm. Actually, I don't mind it. It's a nice function. It looks like that when you start at 1 and go to 9. Nothing wrong about it. But instead, I'm going to look at the integral from 0 to pi over 2, sine of x dx. Now you may say, okay, why the difference? I mean, sine of x between 0 and pi over 2, it also looks like this. So the picture should be essentially identical to an uninformed reader. Well, here is the fundamental difference. I know here that the answer is 1. Here the answer I know, but it's not so nice. So if I use this as an example in Maple, and we get some answer, for instance, a number like that, I will see immediately whether it's good or not. I can check on the error easily. So here I'm integrating sine between 0 and pi over 2. The method is right rectangles, and number of steps is 4, just like we have here in this picture, in this example. Bang. So the formula tells us, or the procedure tells us, that we are using step size essentially 0.4. This is a very useful information. We will get to it. And the outcome is 1.18. Now we know that the correct answer is 1, so it's not all that great. But, well, okay, that's life. And since we are wondering how good it is, let me do a little trick. I will ask for output to be the graph. And Maple thinks that it's calculating this. We can see those 4 rectangles. And we know that the areas of these rectangles are attempting to estimate the area under the graph, and we can see that there is quite a big difference. Okay? So those little triangles here, they are not really triangles, but they sort of look like triangles. These little pieces here, this is actually the errors, and we will get to it soon. And when I use partition size 4, those errors, those extra parts are really, really huge. So I cannot really expect good approximation. Let's try left rectangles. And I think that we will see what we expect to see. We see 4 rectangles, although the leftmost one has a height 0, but it's still a rectangle, okay? Zero rectangle is still a rectangle. And again, we see those empty triangles. These are the errors. That's the area that we didn't account for. And if I ask for the value, I just erase this graph output, then the method of left rectangles thinks that the integral should be 0.79. So the error is roughly 0.21. That's a rather large error. Which brings us to the key question. We have 2 new methods, method of left-right rectangles, and in numerical analysis we always ask, what is the error of the method? Meaning the absolute error, usually as the first step. So we want to know what's the difference between the actual value of the integral and the approximation that we offered instead. There are some interesting points. Well, intuitively, there is a parameter which describes the quality. We saw it with the derivative, we have it here with the integral. And intuitively, this parameter should be the step size h. Why do I think so? Well, let's have a look at this. Imagine that I tell you that I approximated some integral with partition size 2, so I used 2 segments. What does it mean about the quality? Well, let's see. Let's say that my integral looked like that. This is the area that I'm trying to approximate. And if I use partition size 2, then I'm making quite a big error. This is with the right rectangles. On the other hand, if the integrating range was like that, and I used partition size 2, then the error seems to be rather small. So the partition size by itself does not really tell us anything about quality. For quality, for appreciation of quality, you need to relate the partition size and the range of the integral. But that's exactly what this formula does. So the step size is exactly the right measure of quality, just like it was with derivatives. Here the step size is huge and the approximation is quite bad. Here the step size is small and the approximation is much better. Okay? This is, by the way, one of the advantages of integration, numerical integration. You actually see the errors in the picture. Okay, what is the error here? This is the error. This is the error. This is the error. This is the error. These are so-called local errors. Errors in one panel. And we will soon confirm that when you sum them up, you get the total error. You can see it easily here. The total error is just the sum of these 2 guys. So the natural viewpoint is to use h, step size, as the parameter for the error. However, we cannot do it formally in theorems, definitions. Why not? Because we cannot choose step size freely. Imagine that this integral is between 0 and 1. And you decide to use step size 0.4. You start at 0, you go to 0.4, the next step takes you to 0.8, and you are in trouble. Because the next step would take you to 1.2. 0.8, 1.2, these are not good, you need to get to 1. And that's why in theory we have to always start with the partition size, and for the partition size then you develop or derive the step size. So we can think of it this way. We would like to have step sizes as our point of view, but not all of them are allowed. Only some are permissible, depending on the length of the integrating range. And for those special step sizes, then we develop some formulas. Okay, what do we expect? There is something which is called qualitative analysis, when you are not asking about precise formulas, but just influences. So what influences do we see? If I develop some formula, what do I expect to see there? Well, okay, always I see some constant. So let's put it there. Easy. I definitely expect to see the step size featuring in some way. What way, I am not sure. But I do expect to see something here with step size. What else? Well, how do I recognize from the picture and from the overall setting whether the error is small or large? And now let's disregard the step size as a factor. So we have a fixed step size. How do I determine whether the error is small or large from the picture? Well, one influence is the length of the picture or length of the integration range. If it's longer, then there is a better chance of creating error. We make more of them. For instance, if you double the integration range and the function is, let's say, periodic, then you simply double the error. And if you triple the integrating range, you triple the error. So our expectation is that the error will be directly proportional to the length of the integration range. Definitely. This looks like quite a good guess, safe guess. So that's the number of the panels. That's handled with this B minus A. How about individual panel? Can we somehow recognize key factor whether this error will be small or large? I look at my picture and those errors do not look always the same. For instance, here we can see large error, and here this one is much smaller, although this, okay, picture is not quite correct, but these are supposed to be strips of equal width. Well, when you look at this, there is a big difference between the slope or steepness of the function. Let's have a look at it here. You have two panels. On one, the function is steep. On another, it's not steep, it's rather flat, or perhaps this flat. What will be the error? Well, we are using rectangles, we are using horizontal segments to approximate our function. Here the error is outrageous, here the error is reasonable. So the important factor from the point of view of the shape of the function is the steepness or the speed of rise or growth. So what I want to see here is something which talks about steepness, and steepness means derivative. So these are the key factors that I expect to see after I develop some formula for the error. Okay? Now, this error that I'm going to develop will be so-called global error. It will be the difference between the integral, I, and the formula which I obtain, for instance here, from the left rectangle method. And this is what I'm really interested in, global error, and I expect it to look like that. But to get there, we have to first focus on individual panels, because there are those other factors, the steepness, things like that. Width of the panel, definitely a factor. So we are going to focus on just one panel, and to make our life easier, we forget about partitions. We forget that there are 150 panels. Let's have a look at just one. It starts here, it has width, and it ends here, therefore. Okay? There is some function, and we want to approximate this area with an area of just single rectangle. That's our aim now. What error do we make? And this will be a local error. That's our question. Well, the local error is the difference between the area in this one panel and the approximating expression, which could be, for instance, this one. But how do we subtract this number, which is just a product, from an integral? This is impossible to cancel or anything. So in order to work it out, we need to do a little trick. We need to look at this integral that we are trying to approximate and rewrite it in a different way, which is, let's say, more user-friendly, which can be handled easier. And for that, we are going to use a little trick. I'm going to look at it and ask myself, okay, x is a dummy variable in the integral, c is fixed, what is moving is h, the width of the panel. So this is in fact a function of the width h, and as such it has Taylor expansion. How does it look like? Well, I have to choose center. I'm interested in really narrow panels, so I'm imagining that h should be close to 0, so 0 will be the center. F at 0 plus f prime at 0 h plus 1/2 f double prime at 0 h square plus 1 over 3 factorial, so that the reader can see the factorial. And that's enough. I could put 3 dots here, polynomial going to infinity, but I prefer to put capital O h4, which is the notation that we introduced before, and it's very useful. Okay. So that's the Taylor expansion applied to capital F, but we don't really have information about capital F. We have information about lowercase f. So is there a way to go from capital F to lowercase f? The answer is yes. We start here. What's capital F at 0? We put 0 for h, 0 for h. This is integral from c to c, and regardless of whatever comes after this, this must be 0. So it disappears. Wonderful. Okay, how about the derivative? That's a good question. Now, derivative of this expression should remind us of the fundamental theorem of calculus. And there was a formula for derivative of this expression, just with slightly different notation. But it's not so difficult to figure out that if you want to find derivative of this capital F at some number, it's just f at c plus t. So when I apply it, I put 0 here, 0 here, I see that the first derivative here is just f at c. And then this formula can be repeatedly differentiated, and we find that this second derivative is just the first derivative of f at c, and this is the second derivative of f at c, and so on. So we get something that looks like a Taylor polynomial, over here, over here, over here. Just the derivative, the number of derivatives is smaller by 1. So now we are ready to actually evaluate the errors. And for that we will need some room. Okay, let's go for it. Okay, so here is what we just did. We focused on one panel, and we want to approximate the integral over this panel, which we rewrote using Taylor expansion. Now, we are going to approximate this area using a specific rectangle. What will be the error? The absolute error, by definition, and let me just put local here to emphasize it, is the actual value minus the area of the rectangle that we use. Let's say that we use the left rectangle. If I'm using left rectangle, then the area is the base, which is h, times the value at the left endpoint, which is c. And now I substitute from this formula for the integral, and I can see that fch cancels, and the error is given by this tail. 1/2 f derivative ch square plus 1 over 3 factorial f second derivative c h cubed plus o h4. I'm going to simplify in a while, but let's leave it like that and pass to global error, because that's what's important. So the global error depends on the step size, and it's the actual integral that we are trying to figure out minus the method that we use, which is the method of left rectangles. And for that we have this nice compact summation formula. So it's summation from 0 to n minus 1 fxk. Okay, now a little trick. I'm going to split this integral into many integrals over individual segments in our partition. We have a formula for that, no problem. So the integral is actually a summation k passing from 0 to n minus 1 of integral from xk to xk plus 1 fx dx, and I'm subtracting, okay, summation h times fxk, k passing from 0 to n minus 1. Okay, now that's a difference of two sums. We can reorganize it. No problem there. We have a standard tool for it. So it's just one sum, k going from 0 to n minus 1. And let me change the integral a little bit. It's xk to xk plus h, and so on, minus h fxk. And we look at it and we say, oh, wait a second. This is exactly the local error over one panel. So this is a confirmation, mathematical confirmation, that the global error is just a sum of local errors. And we can substitute from our previous calculation. And let's see, what do we have here? The local error is 1/2 derivative, but now the derivative must be related to the panel that we work on. And it means that we have to take derivative at xk. Here we go. Then there will be h squared. That's this term. And once we have it there, we don't really care about the others. So let's lump it into one big O with h cubed being the dominant power. And that's a formula. Now, this can be actually pulled a little bit farther, and one can obtain an answer, but there has to be some tricks used. So instead, I'm going to ask, how large is this? Good question. And for that, we are applying absolute value here, and we can use triangle inequality. By the way, now that I look at it, I think it might be easier for the reader if we group it like that very prominently. So I'm going to apply absolute value to these parts. And after I do that, I get the following. I get inequality, triangle inequality, summation, okay, going from 0 to n minus 1. And then there will be 1/2, of course. There will be absolute value of the derivative at xk times h squared plus OH cubed. Applying absolute value does not change the dominant rate. And now, I'm taking OH cubed, and I'm actually taking it how many times? N times. So this looks good. I would like to use the same trick over here, but I cannot because those derivatives are different for each of the terms that I'm summing up. Another inequality. I'm summing up n times 1/2 times the largest possible value that I can see here. Let's call it m1 times h squared plus OH cubed. Okay? So mathematically, m1, let me put it here, is the maximum of the first derivative in absolute value over all possible candidates. Well, I'm working on the interval AB, so that's the natural place to look at. Is it A? Not quite. Okay. I have to rearrange myself. This is A. Okay. Let me continue somewhere. Let's say here. Why not? So, I'm summing up expressions like that. And now they are all identical, so they're taken n times. So this will be n times 1/2 m1 h squared plus n times OH cubed. What is n? Good question. N is related to the step size by this formula. If I rearrange it, n goes here, h goes down here. They can be just sort of interchanged using algebra. So n gets replaced with b minus a over h 1/2 m1 h squared plus b minus a over h OH cubed, which is, now it gets interesting. Okay, I see 1/2. I see b minus a. I see m1. I see h squared divided by h. And that's it. And here, b minus a is a constant. It multiplies some tail of expansion or some polynomial. It's still a polynomial where the dominant power stays the same. But then I divide by h, and all the powers drop down by 1 in this polynomial or infinite series, power series. So the dominant power will be h squared. That's it. And this is the important part. So that's the estimation for the global error. Here we go. Global error can be estimated from above by mainly this expression. Now you look at it and you see it exactly fits our expectations that we did a short while ago. We can see the length of the integration range, we can see the steepness of the function, we can see the step size h, which is used directly. So there is a direct proportion between the error and the step size. Very interesting. Let's confirm it. This is an important moment. So what do we see here? We have a function f, and we introduced m1 as the measure of steepness, maximum of the first derivative. So the notation fits, I hope. Yeah, it's the same. And then here is confirmation. What we see here in the bracket is the absolute error. It's the difference between the actual integral and approximation using the rule of rectangles, left or right. It needs a little bit more work to do the right rectangles analysis, but it ends up with similar formulas. Actually, you can see that they are the same. There are some little details that are slightly different. Okay, the first formula is theoretical. It is based on the partition size, and I talked about it. This is necessary. But then we pass for chosen step sizes, permissible step sizes, to a, let's say, intuitively more friendly formula which exactly matches ours. So that's confirmation of our work. Wonderful. There are some really interesting things hiding here now. Let's have a look at them. The first interesting observation is this. Our approximation of integral is composed of local approximations over each panel. So there are some steps that we did. We could think of them independently or not, doesn't really matter. Then we put it all together. When we analyzed one component, we got local error. And this local error is of order h squared. Then when we did the overall calculation, the overall approximation, and asked about the global error, it turned out it's a summation of local errors. And when you work it out, you lose 1 power of h. And that's very important. So the global error is just OH. And that's actually fairly typical in numerical analysis. We will see it a few more times in this course. So that's one interesting observation. Another interesting observation is that the global error disappears with power 1, with h. Or you could say it's linear. This is very important, and we talked about it when we talked about derivatives. We would actually prefer to see higher power here, and this was really nice, this h square, but we lost it. That's why this loss of 1 power is sort of sad, because we don't want to lose powers of h. This is a measure of quality of the method. Let me introduce it officially. Here we go. We have a method, not just rectangles, any method for approximating integral. And we find the absolute error, we can see it over here, I minus IN, and we are trying to find an estimate in the form OHP. Now, theoretically, again, we have to work with partition size. And we already saw that partition size and step size, they are related. One is 1 over or reciprocal of the other, more or less, up to this constant. So they are reciprocal. So down here, when we see h to p, we can expect to see 1 over n to p. These are really related. So when you have an estimate like that for absolute error, you say that you have order p for your method. And the higher the order, the better the method. Here, the method of left or right rectangles is of order 1, which is quite good, but not really good. Okay? It's better than nothing, let me put it that way. So this definition is an inspiration for trying something better. But before we get there, let's talk a little bit more about the order so that we can see why it is important. First of all, notice that when we talk about the order of a method, we talk about absolute error, but 2 lectures ago or something like that, we talked about errors, and we said, okay, absolute error is actually not very useful as a measure of reliability. We much prefer relative error. But when you look at books, everybody talks about methods of order P, and they talk about absolute errors. Why is it so? Well, here's a trick, and you should know it, and people who work in the area know it, but it's a little bit unfair that they are not warning readers about this. What is the relative error? Well, it also depends on the step size. According to the definition, it's the absolute error divided by the actual answer, the precise answer. Now you look at it and you say, okay, the precise answer does not depend on h at all, it's just a constant. So when you divide, you still get capital OH. And that's the whole secret. People don't bother talking about relative errors when judging methods, because they know that if they develop some information about the absolute error, it just carries over to the relative error. Okay? So that's why people don't talk about it. I will not talk about relative errors either, but now we know that I'm entitled to it, or that there is a reason behind it. Okay, so that's the important bit. Let's have a look at this formula again. If you don't take it too seriously, if you stop being a mathematician and start being an engineer, you can say that the error is essentially directly proportional to step size h. This is not precisely true, but it works like that for small sizes of step h. Let's make a little side trip over here. I have a code here which is actually finding errors of approximation for the left rectangle method for our integral, but for different step sizes. And I'm going to put all this information into a graph. Okay, so what we see here is the dependence of the error on the step size. And especially on the left, when the step size is really small, that's the interesting part, and it does look like a straight line. So that's very nice, because it fits with what we just derived. In case you are curious about the right part, where step size is larger, it looks funny. This is caused by the fact that when the step size gets larger, there are actually fewer and fewer permissible step sizes. This is actually easy to see. Imagine that the interval that you are integrating over has length 1. Then the largest step size is actually 1. And the next smaller step size is 1/2. And there is nothing in between. So large step sizes, they are actually quite sparse. They are rare. And as you go to smaller step sizes, there are more and more of them available. So I had to somehow take this into account when I was writing down this code. And I chose a way which is not the best one. I know that there is a better one. But what I like about this graph, about this funny part on the right, is that it actually gives us a warning that there are some things happening. And they give us an excuse to talk about it. Okay, so we just did. The most important part here is that we confirm, well, on one example, that the error for the rectangle method is actually linear. And if you use this, you can see direct proportion, which is something that we know from elementary school. This can be used to derive, let's say, relationships. Here is an important relationship. You have a step size, and you change it. Let's say that you divide your step by some number to get a smaller step. You want to improve your approximation. What happens with the error? That's a good question. Well, because the error depends on the step size in a direct proportion, when you divide the step by some constant a, it can be factored, and you find that the new error is 1/a of the original one. And that's important. That's the real meaning of the order of a method. We will return to this a little bit later, okay? But this picture is important. Let me show you how it can be used or what information you can gain from that. Let's return to Maple, to our favorite example. We are trying to approximate the integral from sine of x between 0 and pi over 2. The method is left rectangles. 4 is the partition size. So let me see. I'm going to add something more. I will put output is total error. So that we don't have to think about it. What did I type? Okay, I haven't been looking at my keyboard. So the total error is approximately 0.21. Let me make a little chart here. 1, 2, like that. So when n partition size is 4 and h is approximately 0.4, for the method of left rectangles, the error is approximately 0.21. What happens if I increase the partition size twice? So what happens if the partition size is 8? This means that the step size is now half, because I talked about it earlier. This is a reciprocal situation. If you increase the partition size twice, then you're actually dividing by 2 the step size. So the new step size is, let's say new, h new, is 1/2 of the original one. That's the important thing, the ratio. Well, according to the direct proportion picture, if I decrease the step size twice, then the error should also decrease twice. So I expect to see error here 0.1105. Now I've been rounding up, so let's say that I expect the error 0.10. Something like that. That's my expectation. And let's see what really happens. So number of steps is 8. Bang. 0.10. Here we go. I can actually write it fully here, 0.10. So knowing the order of your method allows you to predict how the approximation, or rather the precision of approximation, improves if you make a change in your setup. And we will get to this later. This is very useful, very important. Okay? For linear methods, this is not all that great, but we will get to better methods soon. So this is the error of the method. We just investigated it. We got lots of interesting information over here. Let me just, for the sake of completeness, attach one more picture. When I was at elementary school, we learned direct proportion, but we also learned indirect proportion. If I take partition size n, and I have some corresponding error, and if I increase the partition size a times, so we can expect a to be an integer, so that it makes sense, then the error decreases a times, okay? So that's a picture for indirect proportion, and here is a picture for direct proportion. These are two very practical viewpoints. Okay, what did we also do with numerical methods? We did error of method analysis. We have a method, we did some experiments, numerical stability. That's an important question. Numerical stability, is there any problem here? Well, when we factor out this step h, there will be just one multiplication. We can see it over here. Multiplication doubles relative error. It's just one multiplication, no big deal. Then there is a summation. Summation does not increase relative error. That's a safe operation. Actually, it's just a formal summation. Could it happen that I'm actually subtracting numbers? Subtracting similar numbers? That's a good question. Well, for that, I would have to be adding a positive and a negative value of a function. Could it happen? Sure. If a function goes from positive to negative and I'm summing up, then I'm in fact subtracting. Now the trick is that subtraction is dangerous at this stage only if those two numbers are very, very similar. Now if function goes from positive to negative and they are similar, they should be almost zero. So I'm subtracting, adding almost zero. Yeah, this shouldn't be really a problem because most likely there are also some huge numbers which will create the result. So I'm not worried about that much. Another possible complication is when you are summing up two numbers which are really, really different in scale. A huge number and small number. Can it happen? Well, actually, yeah, it could happen. But when you are going from left to right, this huge difference would have to mean that the function changes really a lot on a small step. And this does not happen very much with nice functions, with real-life functions. So my conclusion is that the formula itself, the method itself, is actually numerically stable. It's well-behaved. I don't have to worry about numerical mistakes too much. The only complication could actually come from the function itself. And if the function is wild, then I should worry, but I should worry anyway if the function is wild. So that's another topic, okay? We'll get to it a little bit at the end. But let's conclude this whole introductory part of the numerical integration chapter. We developed two methods, rectangle methods. They are not all that great, but they're nice. We analyzed the error of the method, and we learned a lot, especially this trick. This was very useful, so that will come handy soon. And we learned that the numerical stability is not really a problem. So this essentially is an overview of what we will be doing in this numerical integration field. We will try it a few more times to develop better methods, but we will generally follow this outline, okay? Now it's time to develop a better method than the rectangle methods, and I will actually do it 3 times for the price of 1, which is a wonderful deal. But I will actually start with the rectangle methods. Let's have a look at them. In the last panel, we can see that the left rectangle method is actually undershooting, while the right rectangle method is overshooting the mark. On the other hand, when we look to the left, to the second panel from the right, it's the same story, they just reverse their positions. Right rectangles, they undershoot, left rectangles overshoot. So whenever the function is monotone, these two rectangle methods are actually bracketing the correct answer. And as we know, every reasonable function can be split into intervals of monotonicity. So this is actually fairly typical. I have two methods, none of them as itself is exactly great, but they do bracket the correct answer. Why don't I take the average? This looks like an interesting idea. So here is an idea. What is the average? How do you take average? You sum up and then you divide by half. So we divide by half and then we sum up. When we are summing up, again, we can factor out this step size h and what is left. So I'm summing up and the leftmost value is taken just once because only one of the methods really cares about it. But then the next value, x1, is actually used by both methods, the left and the right rectangles. So it's taken twice in the summation. And this is actually true for all the others, almost all the others. We go to the one which is next to the last one, xn minus 1, which also appears here in the summation. And the last value is taken just once. Okay, here we go. So that's the average of these two rectangle formulas, and I think, naively, that it approximates well my integral, hopefully. So that was the first derivation, taking average of upper and lower estimate. Looks like an interesting idea. Let's have a look at another derivation, and we start with a panel. Here is a panel. Let's imagine a function. I'm taking left rectangles, I'm taking right rectangles, and I'm taking the average for this one panel. How does the average look like? Well, it's 1/2 of h of f at the left endpoint, and I think it will be easier a little bit if I put again c and c plus h. So it's f at c plus f c plus h. So what I did here globally, this averaging of two formulas, I did here on the level of just one panel. Let's rewrite it. This is h times fc plus h divided by 2. So what I was really doing is this. I can see product of two values, and one of them is actually the base of my rectangle. So this formula can be interpreted as an area of some rectangle which has base h, and the height is the average of height on the left and on the right. This sounds interesting. You have two candidates, one candidate, another candidate, and you do not know which one to take, so you split the difference, you get the average. I'm actually not taking this as a second derivation. Rather, I take it as a different point of view at this averaging business. But this is actually very hopeful because when I use the average, what happens to the error? Well, sometimes I'm overshooting and sometimes I'm undershooting. So one of these errors is positive, one of them is negative, and they will cancel to some extent. Perhaps not entirely, I shouldn't be too optimistic, but they will cancel to some extent. So I expect this is much better than the previous attempt that we did over here. So that's another justification, but this is still the averaging business. The real trick comes now. I look at this formula and I start thinking back to elementary school. Did I see such a formula before? Let's forget about averaging. Let's really see it as a whole. Did I see something like that before? And the answer is yes. There is a formula about area, which is exactly like that. And that's the area of a trapezoid. When I was at elementary school, they have shown me a picture like that, where h was the height of the trapezoid, fc was one base, and fc plus h was the other base. So I can also interpret this expression, this summation over one panel, as the area of a trapezoid. This is how I was used to see it at elementary school, but let's rotate it. When we rotate it, it looks like this. Here is my panel, c plus h, the width is h. I have two values that I'm interested in. These are my data. There is function passing through, and I'm actually, instead of integrating, calculating the area of a trapezoid. So I'm connecting these two with a straight line and taking this as my approximation. And I'm doing this in a specific panel. I look at it and I say, what is the error? And the answer is, the error is really tiny, much better compared to rectangles. So this is wonderful. And this is actually the starting point for our second derivation of the new method. And I will start from the scratch. Let's forget about it. We have our familiar picture, interval from A to B, our wave function, let's call it f, equidistant partition, some panels over here, and our data, which is over here, 5 pieces of data. Now for the rectangle method, we used step function for our approximation, which means we used on each panel a polynomial of degree 0, a constant function. Natural question is, why don't I try polynomials of degree 1, which means straight lines? Looks much better. Over here, that's a nice approximation by a straight line. And also here, and here, and here. That's a good idea. Or another point of view, instead of rectangles, why don't I use trapezoids? Also a very good idea. Seems much better compared to rectangles. So let's develop our new method, our new inspiration, trapezoids. Here we have the step size. How do I approximate the integral? Well, I have to take the area of the first trapezoid. And again, mentally, I sort of imagine it like that. So it's the height. And now I have to take the average of the bases, which is now the left and right height in this trapezoid. So it will be the average of the value here, fx0, plus fx1. Then we add the second trapezoid. And the second trapezoid is using the value on the left and on the right. So fx1 plus fx2. And we keep going. Now, what do we do next? We factor out 1/2. Done. We factor out h. Done. What is left? fx0 here just once, because it's used only by one trapezoid. fx1 is used twice, because it serves two masters, so to speak. It's twice, and so on. Each value is used by two trapezoids, apart from the last one. This one is used just once. It all fits nicely. So this method can be also thought of as a natural generalization, passing from rectangles to trapezoids in the picture. This is the trapezoid method. And if I click, I sincerely hope it will be there. I recall myself typing it. Here we go. So on the right, we see the familiar formula, all values taken twice apart from the endpoints. And 1/2 and h. Great. Let's try it out. Example. Again, on a test, you may be asked to show approximation of a specific integral using trapezoid method, partition size, let's say 4 per picture. We have seen this before, so let me, oops, our example was going all the way up to 9. Of course, it's possible to do it all the way up to 2, but I don't feel like playing with fractions right now, so I will be nice on myself. Okay, so we have this partition. The step size was 2, and we find the approximation as follows. 1/2, h is 2, and then we are summing up the values. The first value is taken just once, logarithm at 1, twice the second value, which is 1 plus 2 is 3, plus twice the next value, 3 plus 2 is 5, plus twice the next value, 5 plus 2 is 7, and the last value is 9. 7 plus 2 is 9. Yeah, that fits. And as you can see, we are done. Again, on a test, perfect answer like that, I can see what you did. And on the test, you can be also expected to provide explanation for the trapezoid rule, which means explanation. I actually prefer sort of to see this picture with explanation of the area of a trapezoid and how it all comes together. Okay, you should be able to justify the formula, show where does it come from. Okay, so that's the trapezoid method. Very nice. Well, let's have a look at Maple. So I go back to our nice example. Let me go back to partition size 4 and change the method to trapezoid. And perhaps the output could be graph. Of course, we know what the picture will be, but It's nice to see it. Yeah, you can see the trapezoids, and they are much, much better at following the shape of the curve. Wonderful. Total error. That's what we are really interested in now. Here we go. Total error is 0.013. That's a nice number. My favorite is 13, so this is a good sign. Trapezoid method. You can see from the chart that there will be one more method. Anyway, you can see that the error is better compared to the left rectangle point. So it seems that our pictures and our intuition were right. But of course, we would like to see some mathematics. So now we have to erase, make a lot of room, and start thorough analysis of the error of the method for the trapezoid rule. Let's go for it. This will actually be a third independent derivation of our method. We forget about trapezoid rule. We never saw it before. We are just focusing on one panel. Here we have a panel, and we want to approximate in the best possible way the integral of our f over this panel. What kind of data do we have? That's a key question. Well, we know fc plus h, and we know fc. So using these two pieces of data, we want to match this integral as best as possible. Now, with the left rectangles, we decided to use fc. With the right rectangles, we decided to use fc plus h. But you can see the problem. Why use just one piece of data if you have two? Of course, we were wasting our information. So, what is the best way to somehow fit these two guys with this integral? And we don't know, because this integral and those values are of different kind. So, we have to pass two expansions so that we can match behavior. Let's write down expansion for fc plus h, again, when h is really close to 0. So the expansion is fc plus f prime ch plus 1/2 f double prime ch square plus, let me put oh cubed here. Okay, now we have a chance to match, because they are similar in nature. How about fc? Well, it's a constant function. The expansion of a constant function is a constant function. So we have three expansions, and using these two, we would like to find the best possible match for this expansion. So we're essentially comparing polynomials. And obviously, we have a problem here, but we can fix it if we multiply these two rows by h. So I just imagine that I multiply them by h. And you can see that those formulas are now getting much better together. They fit much better together because, for instance, here we can see f prime ch square, f prime ch square. They are much more similar. Wonderful. So how do we put them together in the best possible way? There is an interesting paradox in life that if you have too much freedom, it may actually restrict your imagination, your actual inspiration that you have. Because when you have too much freedom, you don't really know where to start. And if you get some restrictions, it focuses your energy in a certain direction, sometimes against those restrictions, but still you start getting inspiration. So here, if I just ask what expression will work best, there are infinitely many possible expressions. This is useless. This is pointless trying to do it that way. So I'm going to restrict myself to nice expressions because, after all, I don't want to calculate some beastly things with these pieces of data. And the most useful or most convenient expressions are linear combinations. So I will use a linear combination of these two pieces of data and obtain something which I will try to match as closely as possible to this target value. So this one will get multiplied by a constant, this one by a constant, and then I put them together. Okay, what do I get? Remember, I'm also multiplying by h. So, over here I get a times h fc plus h plus b h fc is equal to, they get multiplied by h, this one by a, this one by b, and then I add them, so I can factor out. I can factor out h, I can factor out fc, and there will be a plus b left. And that's it for this line. So everything just gets multiplied by a, by h, and copied. So it will be a f prime c h squared plus 1/2 A f double prime c h cubed plus constant doesn't change the nature of this O, big O expression, but I multiply it by h and raise all the powers. Here we go. So now I'm trying to match these two expressions as well as I can, and we know that the most important term is the one with h, the lowest power. So let's start there. If I want to match these two expressions, then this guy has to be 1. And that's my first requirement. Okay, so do I have a right to arrange this? Yes, I have 2 parameters. I can do whatever I want. Great. The first term is matching. Let's pass to the second most important term, which is the quadratic one. I need, when I compare it, a to be 1/2. That's also an important requirement. And I have 2 parameters, 2 requirements. That's about it. That's the end of the road. So I see that the best match is obtained by taking a and b equal to 1/2. So what is the best approximation for the area under the function on this panel? And the answer is the best approximation is 1/2 h fc plus 1/2 h fc plus h, which is 1/2 h and summation, which is exactly the trapezoid rule. So we just confirmed that the trapezoid rule is actually the best use of information that we have in one panel, unless we want to do some crazy calculations. So the best reasonable use of information, which is wonderful. So this is the third derivation that the trapezoid rule should be good. Okay, now we know what we want to use for approximation, and let's find the error, so the local error. The local error, of course, is the actual integral minus the approximation. So the actual integral we can see over here, and the approximation we can see over here. So let me just mark it into it in some symbolic way. It's the integral minus, and let's call this one, let's say TH, the trapezoid approximation. And now what do we get? We are actually subtracting this series from this series, with the understanding that this is 1 and this is 1/2. So when we subtract, this term cancels, this term cancels, and this term we are not quite sure. So let's write it down. We are taking this and subtracting this, and I can factor out common parts. So there will be some subtraction which is left after I factor out, and I'm factoring out the second derivative of c and the cubic power of h. And from here we have 1/3 factorial, and from here we have 1/2 and also 1/2 for a. So we are subtracting 1/4. Then we are subtracting OH4 minus, and notice here this is OH cubed, but we are multiplying by h, so we are subtracting OH4. And therefore, the local error is, and now it comes. Okay, let me think about it. 6, 4, common denominator is 12. I have to multiply this one by 2, this one by 3, so it's -1. So far, so good. Second derivative at c, h cubed, plus, here is a tail represented by big O, and the dominant power is the 4th power, another tail, another polynomial. When I subtract them, this h to 4 may cancel or may not, I don't know, so I have to play it safe. It's quite possible that h to the power 4 is still the dominant term. Okay, that's it. That's the local error. And now we can do exactly the same calculation as we did for the rectangle method, which means we would look for the global error. We would write down the definition, split the integral into integrals over individual panels, factor out, estimate the second derivative by the maximal possible value, and then use triangle inequality to estimate that this is at most 1 over 12. Then there will be b minus a coming in the same way that it came before. Then there will be the maximal possible value of the second derivative. And then there will be h cubed, but divided by h squared, and some tail. So let me put it just like that. The tail would be OH cubed, which will be less important than h squared. So this is really the dominant part of the error. And again, let's ask whether this makes sense. So we already noticed before that the error should be directly proportional to the integrating range, its size, its length, which is okay. It should be somehow proportional to the step size, and we see that the proportion works with h squared. So this is a better method. It's a method of order 2. That's important. And finally, there is some information about the second derivative. Does it make sense? Let's have a look at it. Here we have a function. We try to approximate by trapezoid. Is it a good approximation? I would say moderately yes. Can I think of a really, really bad approximation by trapezoid? And the answer is yes, if the function looks like this. Then I have a big error. Now, how can I tell apart these two cases? And it's obvious that it's not about the steepness. If a function is very steep or little steep or shallow, flat, this approximation by trapezoid works really well for steep functions, flat functions, no problem. What is really harmful for this approximation is when the function is curving a lot. And this intensity of curving is exactly the second derivative, concavity of a function. Okay? So it really makes sense. Let's confirm it. So here is a theorem. Here is M2, which is a global bound for the second derivative. And here on the left, we have the absolute error of the trapezoid rule. And we can see a formula with partition size. We are not surprised. And then we see formula with step size for specific permissible step sizes. And it fits with the formula that we derived, which is always a good feeling. Okay, so this works well. And again, let's talk about some interpretation. So first of all, we can write that EH is OH squared. It's a method of order 2, very important, which means that in particular, if I use step size h, then with a bit of luck, this error will be proportional to h squared. What does it mean? It means that if I divide the step size by some constant a, now we have to be careful. H has to be a permissible step size, and then if I divide it by an integer, positive integer, then it again is a permissible step size. Then the error will be c times, and now the new step is h over a, and it's squared. So it means that 1 over a squared can be factored out, and we are getting 1 over a squared, the original error. So we are getting a new picture. A new picture looks like this. We have step size and corresponding error. When I divide the step size a times, then the error decreases a squared times. And that's the benefit of higher order methods. Faster improvement, better reaction to the changes that we make. By the way, one can also work it like that. The error, as dependent on the partition size, is proportional to 1 over n squared. And then when you want a better measurement, it means you have to multiply the partition size by some constant a, which should be positive integer. And you can follow similar calculation. Instead of n, you put a times n and you factor out, and you get 1 over a squared en. So this would be like this indirect proportion, but not with constant, but with constant square. Okay, so I could make a picture like that. N, a times n, and the error en changes into 1 over a squared en. So that's another picture that's possible. Okay, let's play. I return to my original calculation that when the partition size is 4, the error for the trapezoid method is 0.013 approximately. What happens if I double the partition size? According to the scheme, doubling partition size or dividing the step size by 2 means I have to divide the error by 2 square, which is 4 times. So that's my estimate. That's my guess what happens with the error in this little part of my chart. So I divide this by 4 and I get 0.003 and something. So that's my expectation. Let's see what the actual error is for partition size 8. 0.003. Yeah, exactly. See, it works nicely. Let me return to this picture when I've been comparing error against the step size. And I talked about some step sizes not being permissible. That's why the picture is so funny. But here I am changing the method from the right rectangles to trapezoids. And let's see the picture. Well, does it confirm that the error behaves like OH squared? The answer is not quite, because, well, I can see this curving shape, definitely, but how do I know that it's h squared? It could be h cubed, or it could be h to 1.1, I don't know, nobody knows. But what we see quite well is that it's not linear, it's much better than linear. This is a very, let's say, hopeful picture, and we can also try another trick. This ratio between errors and step sizes can be checked. And I have a little code here. Let's have a look at it. So in this code, I am going to calculate approximation of my integral for 3 times, with partition sizes 4, 8, and 16. So these are doubles, all the time doubles. I look at the errors, I store them, and then I look at the ratio of the 2 successive errors. So I look at the ratio of errors between 8 and 4, and then the ratio of errors between 16 and 8. And we will actually see this constant. Okay? So first I do it for the method of left rectangles, which is linear. So if I'm doubling the step, I should see doubling of the error. Let's see. Here we go. And we can see the 3 errors. One of them is 0.21, which is in our chart. Then another one is 0.10. And then there is a third one. And we can see the ratio of the 2 successive ones, and it's close to 2, exactly as expected. Now I change the method to trapezoid. Here we go. And again, we see the errors, 0.13, 0.03, exactly as in our chart. Third error, and the ratios are really close to 4. So this seems to work really well. And that's essentially it regarding the trapezoid method. It's a very nice method. Method of order 2 are quite okay in numerical analysis. But for the integration, people were greedy, actually, let's face it. People are sometimes greedy, and they asked, is it possible to do something better? And that's our next topic. Okay, so here we have the familiar picture for the last time, I hope. And a new question, pieces of data. And I'm thinking, okay, can I do better than trapezoids? We started with rectangles, and we used polynomials of degree 0 to approximate our function on each panel. Then we improved to polynomials of degree 1, and we got trapezoids. Notice, when the degree of polynomial was 0, we've got error of order h. When the degree was 1, we've got error of order h squared. Natural question, why don't I use parabolas? Polynomials of degree 2. When the degree is 2, I would expect the error to be of order h cubed. Shouldn't it work like that? Oh, well, of course it should, if mathematics makes any sense. So how about putting parabolas over here into the picture? There is a problem. When you have 2 points in a panel, there are infinitely many parabolas that fit through them. How do you find the right one? It's impossible to solve. Too much freedom. Here is a trick. If the partition size is even, I can split it into groups of 2. And each group of 2 panels, I will call it panel again. It's slight misuse of notation, but okay. This will now be a panel for me. 2 panels, 2 panel, double panel, whatever. I see 3 pieces of data, and through 3 points in the plane, there goes a unique parabola. There is a unique quadratic function which passes like that. Now, what I could do is this. I could split the whole integrating range into pairs of original panels, now into double panels. For each of them, using general data, determine the formula for this parabola that passes through, or this quadratic polynomial. And then instead of integrating f, I would integrate the parabola and get a number, and I would sum up those numbers. And I would get a formula which should approximate the integral. Why won't I do it? Because it's beastly. Okay? I mean, it's not difficult, it's just tiresome. Lots of small calculations. Look at my lecture notes and you will see and you will understand why I don't want to do it here, okay? But it's possible to do it and you get the right answer. Instead, I'm going to do something else. I got inspiration from it. I should focus on double panels. How does it look like? Well, actually, there is a choice how to label it. And if you don't want to get into big trouble, if you want life to be nice, you are going to label it like that. C will be the central point, and you go to the right and to the left by h. And you have your function, and you have 3 pieces of data, and you ask yourself, I'm interested in this area. So we want this. Integral from c minus h to c plus h, fx dx. Now, a little problem. Previously, we developed expansion for the panel between c and c plus h. We could develop a new expansion for this integral, but it's too much work. Instead, I'm going to do a little trick and recycle the results that we had before. Mathematicians were actually the original recyclers. We are really kings of recycling. So I'm going to split it into 2 integrals. One goes from c minus h to c. And this is really boring. I have to keep writing this stuff inside. Okay. And now I'm going to flip these 2 limits, but we have to pay for it by attaching minus sign in front of the integral. Minus integral c to c minus h of the boring stuff, plus integral c plus h, and so on. And now, here is the trick part. This guy is just fh, and this guy is f minus h. Now for fh, we had a nice expansion. How did it go? It was like a Taylor polynomial, but we increased, okay, let me write it down. fch plus 1/2 f derivative ch squared. So the derivative is lower by 1 than expected. That's how it was. Plus 1/3 factorial f double prime ch cubed, and so on. And I will actually have to carry it for longer, unfortunately. Anyway, what we are doing now, we are subtracting. And here we are putting the same formula, but instead of h, we are substituting minus h. So it will be minus fch, because there is no power. Here is a square power, so the minus disappears. It gets swallowed up. Here is a cubic power, so it takes minus h and spits out the minus. Here we go. And then there will be plus, because there is 4th power, and 4th power follows, and so on. So, when all is said and done, and when the dust settles, what do we see? Minus minus is plus, 2fch. Minus plus is minus, this one goes away. Minus minus is plus, they add up. Twice 1/3 factorial f double prime ch cubed. The 4th power cancels. The 5th power stays and it appears twice. 4th derivative, h to the power 5. 6th power disappears, and the next one to appear will be the 7th power. So that's the expansion for this double panel integral that will be my target. This I want to achieve using my data. And I will need a lot of room for it. So I'm going to erase this part and copy the outcome on the top. And then we will get to it. Okay, So what's the pieces of data that we have? We have f, c minus h, we have fc, we have f, c plus h. fc is just fc. For f, c plus h, we had an expansion. fc plus f prime ch plus 1 over 2, okay, f double prime ch square plus 1 over 3 factorial f triple prime ch cubed plus 1 over 4 factorial f the fourth derivative ch to power 4 plus 1 over 5 factorial f fifth derivative ch5. Actually, I should have written f and Roman 5, but I actually like those fancies. I really enjoy, writing them, so I will forgive myself for doing that. Okay, sixth derivative, f1, 2, 3, 4, 5, 6, and OH7. Wow, that's beastly. Perhaps I should have stopped one term earlier. Yeah, I think I could. Okay, I will make it up here, because fc minus h is the same expansion, just for h I'm putting minus h. So it will be fc, here minus f prime ch, here plus 1/2 f double prime ch square, minus 1 over 3 factorial, and so on. Now, plus 1 over 4 factorial. I'm actually beginning to go in automatic mode, which is not exactly okay, because then you make mistakes. I should wake up my brain. Yeah, I give up. Okay. Wow. Okay. Now we can see that there's imbalance between the number of derivatives and the number of h's in these lines. So again, we have motivation. We want to take these 3 lines, these 3 rows, and multiply each of them by h. Definitely. And then those terms start looking similar. For instance, there will be second derivative, h cube. See, it fits nicely. Okay, here we go. The next step, again similar to the previous trick. I'm going to use linear combination of these pieces of data and try to match this linear combination as best as possible to this part. So this one gets multiplied by A, this one by B, this one by C, and then I sum it up. And I get A times H fc minus H plus B times H fc plus C times H fc plus H is equal to, let's go for it. Okay, everything is multiplied by H, factor it out. fc, factor out, what's left? From here A, from here B, from here C. Okay, this one is multiplied by A, this one by C, then they are summed up, and also multiplication by H. So you can factor out the derivative, you can factor out H squared, and what is left is C minus A. The next one, it's similar. I increase the power of H, factor out 1/2, and this time I'm summing up. So it's 1/2 A plus C, second derivative times H cubed. Okay, here I'm subtracting, factoring out 1 over 3 factorial, subtracting, so it will be C minus A. The third derivative, H to power 4. Here I'm adding, factoring out 1 over 4 factorial, A plus C, the fourth derivative, H to power 5. Here I'm subtracting 1 over 5 factorial, C minus A, the fifth derivative, H to power 6. Yeah. Because I'm increasing the power by 6, yeah. Plus OH7, because this tail actually is OH6, this one is OH6, I put them together, and I raise the power by 1. Okay, that should be it. So this is the term that I'm looking for, linear combination of data. This is the term that I'm trying to achieve. Let's achieve it. Okay, here in front of this expression is 2. Here in front of this expression, I want to see 2. The first equation reads, where will it read? Here. A plus B plus C is equal to 2. Okay. H square is missing here, but not here. So this term must be 0. C minus A must be 0. Okay, the next term is the cubic one. I want 2 over 3 factorial, which is 1/3, by the way. So I want this baby to be 1/3. Therefore, the equation reads A plus C is equal to 2/3. Okay. And that's it, because I have 3 parameters and 3 unknowns. So I can make no more assumptions or no more requirements. And then the remaining tail over here and the remaining tail over here, they will create the error. Okay, so there I will have to resign myself to the fate. We will see what comes out of it. Okay, let's see. Over here, from the second equation, A must be the same as C, obviously. And therefore, from these two, I get that A is the same as C, and it's 1 over 3. So far, so good. If A plus C is 2/3, I can put it into the first equation and subtract, and B becomes 2 minus 2/3, which should be 4 over 3. Voila. So that determines how I'm going to approximate a new panel. Good. Now, let's determine the error of the new method, and let's write down what the method actually does. And for that, I will need room. Okay, so let's have a look what's happening with one panel, or rather double panel. C minus H, C, C plus H, our function, 3 pieces of data. Okay, the area is supposed to be approximated by an expression like that, where A and C are now 1/3, and B is 4 over 3. So, if I factor out 1/3 to make my life easier, and if I factor out H out of these guys, then the formula reads F C minus H plus 4 times FC plus F C plus H. And that will be the key for our final work. But before we get there, let me rewrite it once more. I am going to write 2H there, and you will see why in a second. And therefore, there will be 1 over 6 here. So let me start with 2H, division by 6. And here we have FC minus H plus 4 times FC plus FC plus H. That's a different form, which is not really practical, but it offers a very interesting interpretation. This product here suggests that I can look at it as an area of a rectangle. This rectangle has base 2H, which by a remarkable coincidence is exactly the width of this double panel. So here I can see 2H. And therefore, this expression on the right represents height. So I'm choosing height in this rectangle, and I'm taking into account values of function at all 3 points, but not equally. Notice that if I multiply out, it will be 1 over 6, 4 over 6, 1 over 6. These coefficients sum up to 1. This is so-called weighted average. Okay? And weighted average is just like an average, but it means that some of these pieces of information are more interesting or more important than others. And I can see over here that the middle point is 4 times more important compared to the guys on the outside. Or if I lump them together, then they have weight 2. So the endpoints have half the weight of the middle point when the average height, so to speak, is determined. So that's the idea behind this new method. But now let's put it together. We have many, many double panels, but in fact we also have those basic panels. There is this number n, partition size which is even, and then we split this situation into double panels. How many double panels? The answer is actually n divided by 2. This will be handy very soon. For each double panel, I'm going to use this approximation, and I sum them up. So the integral gets approximated by, from the first double panel, there will be 1/3 h, and there will be the first value, f, which is actually this point on the left, which is fx0. Then 4 times the point in the middle, which is x1, and the point at the right endpoint of this double panel, which is fx2. Then I add another area for double panel, which comes after that. This is x2, x3, x4. So I'm taking the one on the left just once, fx2, the next one 4 times, and the next one just once. x4, yeah, x4. And I keep going. What happens? That's interesting. The guy on the left is taken just once. Poor guy. The next guy is taken 4 times because it's the middle of a double panel. A very important guy. The next guy is on the edge of a double panel, but it's actually shared by 2 double panels, so it's taken twice. So it's like medium importance. The next guy is in the middle of a double panel. It gets taken 4 times. The next guy is shared. It's taken twice. You can see the pattern. 4, 2, 4, 2, 4, 2, and so on. And you keep going until you reach the second last guy, which is in the middle of a double panel, so it's 4 times. And the last guy is taken just once. That's the new method. This is called the Simpson method. Here we go. I would be very surprised if we see something else. Yeah, Simpson rule. This is called by somebody called Simpson. It was a guy who was actually employed to estimate the volume of ships based on some measurements for the British Admiralty. So this was actually a very practical method. Does the pattern agree with ours? Yeah. 1, 4, 2, 4, 2, 4, 2, 4, 2, and 1. And there is some attempt to write it down using summation notation, which is, I mean, it's perhaps a little bit more compact, but it's less transparent. So I'm not sure it's actually any progress there. Okay, the Simpson method. How good is it? We confidently expect this method to be of order 3. Let's have a look at local error. What is the local error? Well, the local error is definitely going to be this series, and from that we subtract this series. Definitely. So, 2 here, cancels. Good news. 0 here, cancels. Good news. 1/3 here, 1/3 here, cancels. Good news. The next term will create the error. 0 here, C minus A here, which happens to be 0. This is a big piece of luck. Normally, this h to the power 4 would be the local error, but because the situation is symmetric, this power disappeared in our target formula, but it also disappears in this linear combination because A and C are the same numbers, they are equal. So actually, or even powers in this expression will be 0 automatically. Amazing. So what is the first non-zero number? Well, we don't really know yet, but the good candidate for the first non-zero number is this one, the 5th power. We have to work out whether perhaps this number and this number are different or not. We don't know, we have to calculate. So the local error is, let's see, I'm going to factor out the 4th derivative and the 5th power, and then there will be something left in the bracket. And in the bracket, there will be 2 divided by 5 factorial minus 1 over 4 factorial, and a plus c happens to be 2/3. Times the 4th derivative, h to the power 5. And now the trick is that the 6th power disappears and the error is OH7. This will play some role later on, that in the error also the 6th power is missing. But right now we don't really care. We could have written OH to the power 6 and it would have worked perfectly. Okay, so no problem there. I just don't want to lose information if I already have it. Okay, how much is this one? Okay. Let me think. Okay, little thinking corner here. So the common denominator should be 5 factorial definitely, because here I cannot create 5 in any way, and 3, extra 3. Now to get this, I would have to put 6 over here, and 10 over here. Okay, I need larger thinking corner. 6 minus 10 is negative 4 usually, over 3 times 5 factorial, which is, okay, 4 cancels, 2, 3, 5, 2, 3, 5, 10, 90, 1 over 90, 4 over 90, 1 over 90. Is that right? Yeah, 1 over 90. So the local error is minus 1 over 90, the 4th derivative times h to power 5 plus OH to power 7. Okay, let's see the global error. Now the global error can be estimated by, and now it gets interesting, we have to be careful. We have to sum up local errors for every double panel. How many double panels are there? The answer is n over 2. That's a change. Before we were putting it n times. Now we put it n over 2 times. So we take n over 2 and we put upper estimate for the local error, which is 1 over 90 times the maximum of the 4th derivative times h to the power 5. Let's ignore the O part. We will ignore it anyway. Okay. Now we substitute for n. N creates b minus a. So it's 1 over 180, b minus a. Then there will be m4, and 1 power of h cancels. So the conclusion is that the global error is OH to the power 4, which is better than we expected. This is a bonus for the symmetry of the situation. And by the way, if you decided to try triple panels and a cubic polynomial, then there is no bonus, and you would really get OH to the power 4 as expected. Okay? So this method actually has the same quality as approximation by cubic polynomials over triple panels, but less work, which is wonderful. So this method is actually very useful. It's one of those default methods. If you want numerical integration, this is a good candidate. Okay, we just found an estimate. Let's confirm it officially and then ask what does it mean for us. Okay, so we can see, let's go right away to the end. 1 over 180. Okay, I got lucky. I don't always get it right. Sometimes I make a small mistake and then I have to do it again. So yeah, I am feeling really great now. M4, b minus a, h to the power 4. Yeah, everything fits. So I got it right. Wonderful. Okay. I didn't do an example by hand because I'm not going to ask for Simpson method on a test by hand. I don't think there is much point in it. Computer can do it better and faster, whatever. So I guess I can save this room for a little story. Okay, we have step size. We decide to divide it by some integer, positive integer a. The original error gets divided by, and now let's just imagine that here instead of h to the power 4, we put h over a, that all to the power 4. So 1 over a to the power 4 gets factored. And that's the real beauty, that's the real strength of the order of a method. It's not that trapezoid for the same n gives you a better answer. This could be an accident. And sometimes it's actually the other way around. Sometimes a worse method can give you for a specific step better answer because it likes the problem. This can happen, okay? Fatal attraction. But the real heart is at the improvement. Here, when you double the step size, double the partition size, the error gets halved. Here, it got divided by 4. For Simpson, it gets divided by 2 to the power 4, which is 16. This is wonderful, okay? Let's try it out. Okay, here we go, Maple. First of all, let's go back over here. Simpson. Number of steps 4, output error. Here we go. So the Simpson rule, wow, that's also nice. 0.0013. I like that. Okay, did I miss a 0? Yes, I did. There should be 3 zeros after the decimal dot. Yeah, now it fits. It's a little bit more. I'll have to take this into account. Okay, let's make prediction. This is the error for partition size 4. If I double the partition size, this gets divided by 16. So it will be 0.00000. 130 divided by 16. 7 is not enough. 8 is almost there. 8. It will be a little bit more, but not by much. So that's my prediction. 1, 2, 3, 4, 5 zeros and 8. Now I am really apprehensive. Okay. Yeah, it's there. Okay. 5 zeros and 8. Good prediction. It works really well. So that's Simpson. Wonderful. And as you can see from the chart, the error for Simpson with the same starting data, 4 or 8 partition size, gives much better answer for essentially the same work, because the only thing which changes is this 1/3 over here. For rectangular rule, there was nothing. For trapezoid, it was 1/2. So there is tiny change. And slightly different set of coefficients. That's the only change in the formula. And you get much better approximation. Let's have a look at this trick with ratios, okay? So when I use Simpson rule as the method here, and again, 3 partition sizes, 4, 8, 16, and we will compare the errors. And we expect to see 16 as the ratios. And we do. Notice that the second ratio is closer to 16 because the smaller the step size, the better all these things work, okay? For larger step sizes, they work just like approximately, but for smaller step sizes, much better. Okay. I didn't try this picture for the Simpson method. You know why? Because we couldn't tell any difference. I commented on this before. This is just like a curving something which could be h to the power 17 for all we know. So instead, I'm going to show a different picture, this one, which is a comparison of the trapezoid error and Simpson error. And when you look at it, the trapezoid error in blue is much larger than the Simpson error in red. This doesn't prove anything, but it's a strong suggestion that the Simpson method really has a much, much smaller error. You can see that it sort of hugs the h-axis, which is a significant hint that the power that we see here for the red curve is higher than the power for the blue curve. Okay? So that's essentially it. Let me just put some survey slide over here. This is an overview of numerical integration. We see our 3 methods: rectangle, trapezoid, Simpson, and the important part is the order. We can see the jump for the Simpson method as we commented. Now, there are still some interesting questions unanswered, so I will go on. One interesting question is, how do I get the error and how do I work with the error if I don't know the answer, like I did in the examples in the Maple? Key question, so I will get to this, and at the end I will show a few more ideas for some other methods that can be used. Okay, let's make some room. And now it's time for a key question of numerical analysis. I'm supposed to figure out some integral I, so I choose some method, I choose partition size, and I produce a number, in, which hopefully approximates well the integral. But how do I know if I don't know the precise value of the integral? What is the error? That's the key question. And we had a video on Richardson extrapolation, which works with step size. But this is not a problem because partition size and step size, they are related. But it's actually worthwhile to transform the results of the Richardson extrapolation into the language of partition sizes because it's very useful for integration. Now, I could do it right away without any trouble, but I think it's good to recall the basic idea and show it in the language of partition sizes. So, here is a piece of real line, and here is I, the number that I'm trying to achieve. Now, I will do two experiments, one with partition size n, and the other with partition size 2n, so I can expect it will be better. So the partition size 2n will get me closer, while the partition size n is still not so precise. That's a typical situation. And I'm interested in this error. Okay. I look at it and I say, wait a second, there's also another error here. And if the IN is a method of order p, then I can expect that this error is actually 2 to p times e. We talked about it earlier, how the order of a method transforms into the changes in the error. So when I go from here to here, the partition size is divided by 2, and therefore the error is multiplied by 2 to p. And then I look at this distance and I say, okay, I2n minus In is 2 to pe minus e, and a little rearrangement, I factor out e, leads me to the formula that the error can be perhaps I2n minus In divided by 2 to p minus 1. And we also, in this video about Richardson extrapolation, derived a formula for better estimate of the integral, which I'm not really interested in right now. So I think I typed it. I see myself typing it. Okay, here we go. So we have a method of order p, which is specified a little bit better in the formula there. And then there is a formula for better approximation of the integral. And the last row, this is the formula for approximating the error of I to n. And the formula fits. Okay, so first of all, let's have a look whether this really works in applications. So here is an experiment. We have our favorite integral from 0 to pi over 2 sine of x dx, which is actually equal to 1, so we know. I'm applying the formula for left rectangles, which has order 1, and I will calculate the actual error and also the Richardson extrapolation, and I'm using step size 4 and double 8. Here we go. So, when the step size 4 is the test value and step size 8 is the one that I'm interested in, then the one that I'm interested in has error 0.101 essentially, and the Richardson estimate based on I4 and I8 yields 0.107, which is fairly close, so it seems that it works. Okay, let's try to change the method to trapezoids. And therefore, I have to also fix the order. Trapezoid is a method of order 2. And again, there will be 2 attempts. One of them when n is equal to 4 and n is equal to 8. This will be the 2 attempts. This one is the one I want. This one is used for estimating the error. Bang. And again, we compare these 2 numbers, and they are fairly similar. The first 2 valid digits, they agree, which is very nice. And finally, how about Simpson? So the Simpson method has order 4, and again, let's fire it up. And now these are really tiny errors, and again, the Richardson estimate works reasonably well. So this is something nice. Now, to conclude this very short section, let me show you something. I will use trapezoid method, And I'm interested in what happens when n is equal to 8. And I will use Richardson estimate. And I will do it by hand so that you can see what I'm actually doing. So here I calculate using the trapezoid method with number of steps 8, okay, I think I can skip this one. The integral, roughly. And the value, I8, is about, here we go, 099, let's see, 6785. I can stop here. If I stopped earlier, I would have to round it up to 1, which is the precise value, of course. Now, I don't know what's the error. I actually know the actual value, but I pretend that I am not aware of it. So, if I want to estimate the error, I have to make first a test run with half the step. So I'm going to save this result to a variable called I2 because it's the one that is more precise. I2 is this, bang, it's there. Now I'm going to do another calculation, the one which is preliminary, I1, which is number of steps 4. And here the result is 0.97 and so on. And now I use this formula. Now the order for trapezoid is 2. 2 to 2 is 4, minus 1 is 3. So I will be dividing by 3 and subtracting. Let's have a look at it. So the error estimate is I2 minus I1 divided by 3. Here we go. This is the error estimate. 0.00322 and so on. Now, imagine the following situation. You have a customer, and the customer says, okay, what I really need is an approximation of this integral, and my requirement is that the error is less than 0.00001. How do I do it? Here is the trick. When the partition size is 8, I get error, which I don't know, but it was estimated. Estimated using the Richardson's formula, which we have over here. Now, I argue this way. If I increase the step size, the partition size 8 times, then the error decreases a squared times, because it's a method of order 2. And the requirement is that this should be 0. How many zeros? 1, 2, 3, 4. 4 zeros. 0.00001. This is the requirement for my customer. Well, that's an equation from which I can determine A. How much is A? If I call this one epsilon, which is sort of customary, the required precision, then A is equal to, and I rearrange it, is the estimated error of my first attempt divided by the required precision and square root I take. And I get A, and if I know A, I know the new step size, which is recommended to be used. So let's have a look at it. What is A? A is square root of the estimated error divided by the error which I'm supposed to have in my calculations. So A is about 17, but I need integer, so I round it up. I round it up because I get bigger partition size and more precise answer. So my new attempt will be using n, okay, let me put it just like that, 8 times 18. That's my new recommended partition size. The original partition size was 8. I multiplied by this 18, and I get, let me see, 144. So the new recommended partition size is 144, and just to be on the safe side, I take 150. Okay? This shouldn't make things much longer. And I hope that it will give me what I need. So I go back up here, and I use number of steps 150. And I get some result, which I stored in I2. And this result, you can see it over here. Now, would I know that it's correct? I am not sure. So I will try the Richardson estimate again. So I will have to make another experiment with just half the partition size, which is 75. And I have it over here, the code. So partition size 75. And again, I use the error estimate. And the error estimate is 9 times 10 to negative 6, which is a little bit smaller than this one. The error estimate is 0.123459, which is almost 0.12341. That's exactly the requirement. So Richardson estimate of error tells me that this could be the answer that my customer wants. Just out of curiosity, is it true or not? Let me look at the actual error. So I2 is the result which I want to hand in to my customer. And the absolute value of the difference between I2 and the actual value is, voila, it's almost the same as the, it's really almost the same as the error estimate by Richardson. The last line and 2 up, these are almost the same numbers. So this is actually something which is practical. You see, I wasn't cheating. I never used the fact that I know that this integral is 1. I made an attempt using the Richardson estimate and sort of like half-quality attempt. I estimated my error, and I used the knowledge of the order. This is what I call this indirect proportion, but it's not true anymore because there is this square happening. But this scheme is very helpful. So I use this scheme and the requirement on the error to actually determine how I should modify my step size. And the modified step size actually gave me the answer that I needed. So in applications, it would be too wasteful to simply try increasing n until I get lucky enough to get the right answer, because I could be trying n equal 8, 20, 100, many experiments. In this way, I got it in one step. Very nice. So that's very practical, and it shows that the Richardson estimate not only gives you valid information, but you can also use it to actually predict what's going to happen with your experiments, and you can focus and just zero in on the right answer with very few attempts. Okay? Very nice. Okay, I think we are ripe for the last part of this lecture. So these methods are, from the point of view of numerical stability, quite okay. We do not have to worry about it. However, as I said, we do have to worry about, let's say, not friendly functions. And that's the moment when people start thinking that perhaps some other methods might be interesting. All these methods that we saw, they fall into one category. These are called Newton-Cotes methods. And they are based on this idea of equidistant partition and things like that. Now, there are some alternative ideas. Let me just quickly show you some outlines of, I think, 3 interesting approaches. The first approach starts more or less like these methods that we have here. So you have an interval, a function on it, and you take a division. Now, on one panel, what we usually did was either to use the values at the endpoints to determine our height, or we combine them somehow. For instance, the trapezoid method, it took the average of these 2 values. There is an interesting idea. Instead of looking to the left or to the right, we look in the middle of each panel. I look at the value of the function here and use it as the height for my rectangle. Now, of course, this is cheating because we are supposed to sample our function exactly at the partition points. So this is cheating, but it's an interesting idea. And it seems to make sense because if you are taking value in the middle, then most likely the error will be positive on one side and negative on the other side, or vice versa. So there is a good chance that these errors will cancel each other out to a large extent, and this looks like a potentially very interesting method. The integral would be approximating by the base of each panel, which is h, and then I take the value at the left endpoint, but I shift it by half the segment. And I take the next value, and shift it by half the segment, and so on. And I take the xn-1 point, which is the one just before the last one, and I shift it by half the segment length. And that's it. This is the midpoint method. So as I said, this does not really fall into our group that we covered, but it's very similar, so people very often just put them together into one big group and they say, okay, they belong sort of together. This method is also of order OH2. So it's as good as trapezoid when it comes to the growth of the error. Now, in practical applications, they are more or less equal, but there are some differences. People actually have a reason for using this method. It's a good one, and it will come handy when we start talking about differential equations too. So that's one of the reasons why I introduced it here, so that you can recall at least the basic idea later on. Okay, let's move on. I have a function. I have a partition over here. I have lots of points. And what I did, I split it into groups, and I used a quadratic polynomial on each group, on each double panel, or I could split it into triple panels and use cubic polynomial and so on. And the natural idea is, okay, why don't I just give up on any splitting? I have a bunch of points, so I can put a polynomial through them. And if I have partition size n, then there is a unique polynomial of degree n. There is a unique polynomial of degree n that passes through all these points. And then instead of integrating the function f, I can integrate a polynomial, which is easy. Everybody can integrate polynomials. And I get estimation of my integral. This looks like a good idea. It's not a bad idea, but it has a problem, because if you start increasing n, then you run into a problem of oscillations in the polynomial. Polynomials of high degree, they love to oscillate. And it totally spoils this approximation. I will be talking about it more in the video on interpolation. There is a way to fix this problem, and this is something which is called Gaussian integration or Gaussian quadrature. And the trick is that you do not take equidistant partition, but you put more points towards the ends of the range. So you add points here, add points here, add points here, and so on. But you do not do it randomly, or like some layperson just putting some points. You have to do it in a very sophisticated way, and then you get a method which is really good. This Gaussian quadrature. And I cannot really describe how those points are chosen, because I will have to spend another lecture or two on covering some background, because this is based on some quite advanced topics of mathematics. But it's an interesting idea to use a polynomial. Yeah, why not? And for the last, my favorite method. You have a function. And one problem of those methods that we covered so far is that those dividing points, they are done according to a scheme. So they can be predictable. We can predict where they fall. And if the function decides to play tricks on you, for instance, by playing with some needles and things like that, it can put those tricky parts into the places where your sampling points are not going to fall very often. And you can miss out on this trick. You can miss out on those problems when you are using regular partitions. So there is an idea. Why don't I simply throw in some points, a bunch of them, a lot of them, quite randomly? Well, of course, then I cannot use the usual formulas, but I can still erect rectangles over these segments. They are irregular, so I cannot use, let's say, summation formula. I have to simply calculate each of them separately and sum up the areas, but that's not a problem. That's not a problem when you have a computer. So this can be done very efficiently. And you calculate an approximation of the area using some random sample, and you store it, you store this answer, and then you try it again. Again, different random distribution of points, and you calculate the approximation, and you look at it, and you compare them, and you do it a few times. And if all the answers agree, then you have a good chance that, or more or less agree, then you have a good chance that you have an approximation of the integral. But if one of the answers is suddenly different, markedly different, then this is a suggestion that the function actually has some tricky parts, and this one partition, which is different, actually hit on those tricky parts. So it points you to points where you should investigate what's happening, and you have a chance to improve your situation and to handle the problems. You actually discover them. And this, because you do it by random, we are actually playing games, this is called Monte Carlo method. And that's why it's my favorite. I've never used it actually, but I just like the name and the idea. You're just playing dice or whatever, hoping that something nice will come out of it. Yeah, there are actually some applications where people do this, which is even more amazing. Okay, I guess that's about it. And this is really the end of the chapter called Numerical Integration. And we keep going. And the last rectangle takes as its height the value at the very end, at number b, but actually we prefer to write xn. So as you can see, these two methods, the method of left rectangles and the method of right rectangles, they are given by essentially the same formulas.